Hello, everyone. I'm Anup Kumar. I work with the Freiburg Galaxy team in Germany. In this demo, we will look at an interactive tool running in Galaxy Europe. This interactive tool opens a Jupyterlab notebook. This Jupyterlab notebook is GPU enabled, and lots of machine learning models can be created with this notebook, apart from many other features such as Git integration and workflow of notebooks, and so on. Jupyter Notebooks, as we know, it's a popular editor for many tasks, such as computing scientific data, and also used for data science projects. It can also be used for machine learning projects using scikit-learn, TensorFlow, PyTorch, Keras, and so on. In all the 3 points that we discussed, they all contain some kind of data analysis. And there are lots of packages Jupyter Notebooks contain, such as scientific Python, then stats model, then NumPy, and many other packages which can be used for scientific data analyses using Jupyter Notebooks. It can also be used to show how to learn code, for example, in Python or in R. It does not require any installation of required packages to learn Python and R and for doing other analyses. It already has lots of packages installed. Therefore, because of these packages which are already there, prototypes of many projects can be created in a swift way. These Jupyter notebooks can be made to run on web, and using a link, it can be shared with any other user. How did we develop such a tool? The tool pulls a Docker image. The Docker image is derived from a base container. This base container comes from a Jupyter/TensorFlow notebook. This base container contains lots of packages such as scientific Python and NumPy, Python, and many other packages already. On top of these packages, we have made the image to run on GPUs by installing CUDA and CUDA DNN deep neural network packages. These packages support NVIDIA GPUs on the machine it's running. And for using deep learning, we have installed TensorFlow GPU package. If on the host machine, if there are GPUs installed, then the program written in TensorFlow will automatically run on GPUs. And then this Docker image serves Jupyterlab automatically. This Docker image is separate from Galaxy. It can be run on any machine. The image can be pulled and can be run on any machine. If there are GPUs, the programs in the notebook will run on GPUs. Otherwise, it will just run on CPUs. After building this Docker image, we have created a tool, interactive tool ML Jupyter Notebook, and it is hosted in Galaxy EU. This notebook pulls the Docker image that we just discussed and then creates a notebook job that keeps running. As long as the job is running, the Jupyter notebook is open. And then while this job is running, it pulls the Docker image and serves a Jupyter Notebook Lab on web. We will see how we create such a notebook job, and then this job will open our Jupyter Lab notebook. Let's look at the important features of this notebook. For faster computations, this is GPU enabled. If the host machine it's running, it has a GPU or multiple GPUs, The programs can be parallelized, and deep learning programs, we know they run on large data sets. Therefore, to make the programs run faster, GPUs can be harnessed and the program can be accelerated. There are lots of pre-installed packages for machine learning, such as scikit-learn, tensorflow for creating machine learning models. Then we have pandas for data manipulation. We have HDF5 store to store the matrices if we have. Then we have a few plotting tools such as matplotlib, seaborn, and Voila. We will see examples of all these packages. One of the important features of this notebook is its integration with Git version control. We can import any Git repository from GitHub, and we can edit all the files and import data, and then we can push them back once we are done. And then it can be maintained, the versions can be maintained of each file, just like we do elsewhere in our machines with GitHub. Another important feature of the tool is that it can create exchangeable and shareable model for machine learning code. This has been made possible by using ONNX models. This is a standard open neural network exchange. These models can be reused and saved and can be shared with anyone. And once these models can be created, they can be downloaded and reused again for inference or for extension. These models are available for scikit-learn models and for TensorFlow as well, and for PyTorch and for Keras as well. In our notebook, Jupyterlab notebook, let's suppose we have lots of notebooks and we want to create an entire analysis or pipeline of these notebooks. This is possible also in the Jupyterlab interactive tool by using Elira AI. Using a pipeline editor or workflow editor, just like we use in Galaxy, many notebooks can be connected with one another and the entire pipeline can be created for an end-to-end analysis. This whole unit can be run once and we can get results at the end. We already know Galaxy community provides BioBlend APIs. With these BioBlend APIs, we can connect to Galaxy and access histories and workflows and datasets. This is also possible in the notebook. With the BioBlend APIs, it can connect to Galaxy and import histories, datasets, and workflows. There are other miscellaneous plugins that come with the Jupyterlab tool. For example, there are plugins for monitoring CPU performance, then memory usage and GPU utilization. There are features which can be used to collapse and expand sections in the notebook, which is very handy when the notebook is quite big and some sections which we are not using, they can be collapsed, and the sections which we are working on, they can be expanded. We also have a variable inspector for a notebook. All the variables, these values of these variables can be seen in a different tab. It's good for looking at the real values of our variables in the notebook. Also, we have logout button, which takes you out of the notebook, and for expert users, we also have kernel spy, and using this the message passing from kernel, from notebook kernel can be seen. This is the first look of the Jupyterlab notebook. We have the home page here, which explains the core features. And on the left, we have the notebooks and the data stored. On the right, we have these logout button and the CPU usage plugins. Here are the resources which can be used further for looking at this tool and possibly extending it. This link will take us to the interactive tool in Galaxy. Then here is the Docker image of the entire package, which can be pulled using the following command. And it can be run in two ways. If there are GPUs on your machine, we can run it using this command by editing the local folder. We can create a local folder in your machine, and then just give that path, and then the whole command will run. And this is for the machine fitted with GPUs. If there are no GPUs, then --GPUs all should be removed, and it just should run with this command. The code base for creating such a Docker image is present here in this link. And these commands are also discussed in the README page. We also have a running notebook here. We can use it for looking at the notebook. Let's start from the beginning. Tool running on Galaxy. We will copy this link and go to a new tab and open the link. This interactive tool, just like any other Galaxy tool, will run a job. And you already know on the right, you have the Galaxy history, where all the running jobs are shown. Here on this view, we have the definition of the tool open, and then we just execute the tool. Executing this tool will create a data set here. Currently, this particular data set is gray, which means it has not started running. It turns yellow, which means it started running, and soon after that, we will get a link to the Jupyterlab notebook here. See, this has turned yellow, which means this is executing. It will keep executing as long as our notebook is available. There is one more place where this notebook can be accessed. One is here. We click on the link, and this will generate a Jupyterlab notebook for us. This link is totally shareable. You can share it with anyone, and the person will see the same view what you are looking at. Here, we already have the notebook available with us, with all the notebooks on the left, and there are lots of features shown as tabs, which we will look very shortly. Let's look at another place where these links of the active interactive tools are present. This particular view gives a permanent link to the notebooks. As long as this job is running, and these particular links will be available. To remove this particular job, we need to select it and put it at stop. When we stop a link, this job will be finished and particular link will be gone. These links are permanent links here. Let's go back to the Jupyterlab. We will open the home page, which we saw in the presentation. This homepage describes many features briefly. For example, this particular notebook works with GPUs, and there are lots of plotting tools which are available, and data manipulation packages, and machine learning packages such as scikit-learn and tensorflow, and model sharing and Git and so on. There are lots of notebooks available for each of these features in the notebooks folder. We go and open this folder and we see that there are 7 or 8 notebooks available and they are appropriately named. Let's look at the general features of this notebook. On the right, we can see that we have a logout button, which takes you out of the notebook. Then you have CPU and memory usage statistics view. On the left, there are lots of tabs which are available. First one is the file browser, which we saw here. This is the home view. And then how many tabs which are available. There are 2 tabs which are available here and gives information about all the tabs. Then we have this feature for looking at the usage of the system resources such as GPUs and the whole machine on which this tool's job is running and the GPU memory we are consuming and so on. These buttons will are clickable and then it will open one particular tab and it will show a utilization graph when we are actually utilizing the GPUs. Currently, we are not. The status of GPUs can also be seen using a command NVIDIA SMI. Since we have NVIDIA GPUs, we can use the NVIDIA-SMI command to look at the usage of GPUs. For example, the memory, what we have is 15 gigabytes, and we are using only 3 megabytes, and the utilization is 0. Currently, we are not using it. And there are some other information about the GPUs. For example, what is the version of CUDA and so on. Then we have another integration with Git plugin in this notebook. We can clone a repository by clicking here, clone a repository. We should give a link, and we will. Let's look at by importing one particular folder. Before doing that, we need to create a folder here. Let's create a new folder, which is called Git folder. And then inside this folder, we will clone a repository. We will go to this particular link and find the Git link and place it here. And then we clone. We saw that in the Git folder, it's already cloned, this notebook repository, and we have some notebooks and data sets available. And just like we use a GitHub, we can update these files. For example, we update this particular file by writing something, and then we go to the plugin here, and then we see that this particular file has been changed. And then we add it to stage this change in the stage folder, and we can write a command updated file, and then we can commit it. For this, we need to provide our credentials, and then it will already check in the code. This is how we can use the Git plugin. There are other features which are available, for example, for Elira AI, which we will look at the end. Let's go to the notebooks. We will close this and go to the notebooks, which we have not in the Git folder, but in our notebooks folder. Let's start looking at the simple notebooks. first. This particular notebook is for pandas package, which is used for manipulating data sets. It can also be used for plotting graphs as well. We see that this package is being imported using import pandas as an alias name, and NumPy is also being pulled here. For running the whole notebook, we go to the Run tab and click on Run All Cells. And then we see all the cells are now available again, along with the results. Another way to run a particular notebook is to click on Voila. This Voila shows all the results without the code snippets. We can see all these results which are available on the left are also available here without the code snippets. Similarly, we can see another. So we just close it and click on plots, Matplotlib's notebook again. In this notebook, we are using Matplotlib as the plotting library and plot lots of different kinds of plots. We can also run it via Voila. It will take a few seconds to run because there are lots of sections here. We see all these plots are getting generated without the code snippets. There's also a small feature which can be used. It's a render on save. When you check it and and when the code for the plots are saved again, then this particular section will be regenerated. I mean, it regenerates the whole tab and our plots get updated. Similarly, we have another plotting notebook with Seaborn. It's another popular plotting library, which is heavily used in data analysis and machine learning field. We can also run these cells by clicking on the play button. You just click on play button and run all the cells here. There are lots of plots available in these notebook. So running it all takes a few seconds. Alternatively, we can run it via Voila, and it will again create a separate tab and generates all the plots without the code snippets. There is another plotting tab package in the BQplots tab. Before looking at BQplots, we can just browse through the results of Seaborn, and we see all the plots got generated. Let's just close it. BQplots give plots as interactive, and for this, separate widgets are already loaded in the Docker container. And let's run these sections for BQplots, and we will have three kinds of plots here. These plots are a bit interactive. We have this pan button where we can use this, and we already have a save button downloaded. We can also refresh this plot and reset it. We also have a scatter plot, and we can update the data sets of these plots, and then the plot will regenerate itself. Similarly, in the bar plot, we have this plot available, and when we update the data of the plot, it will regenerate itself. This was all about data manipulation and plotting techniques. Let's look at some machine learning notebooks. So before looking at, let's just close all these notebooks so that we have more space. This notebook is dedicated to scikit-learn. Scikit-learn offers many different algorithms for classification, regression, clustering, hyperparameter optimization, then data preprocessing, and so on. So we have discussed in this notebook some of these models. For example, some models in classification, some model for regression, and then hyperparameter tuning and clustering, and so on. We import all the required packages like this and create our models. For example, a linear model called logistic regression is being created here. And then we have this classifier, and we train this classifier, and then we find the accuracy. To run this notebook, as all other notebooks, we go to run all cells, and it will generate the numbers for us for each algorithm. This notebook shows the basic usage of scikit-learn packages, but there are many more algorithms available in scikit-learn which can be tried out in this notebook. Similarly, we have a notebook dedicated to TensorFlow, which gives a way to create deep learning models. And it also uses the power of GPUs for accelerating the program's execution. TensorFlow allocates all the memory the GPU has. To avoid this situation, we should restrict the memory which TensorFlow uses for a program. Therefore, we will import the TensorFlow package, and then we will run this particular piece of code to limit the growth of memory for TensorFlow. To look at the memory usage of the GPU, we see that it's still 3 megabytes. When we allocate 5 gigabytes here, it will increase, and we will see that shortly. Let's go to the terminal and see whether this memory has been allocated. We see that the memory has been allocated what we intended here from this piece of code. Now, we can also load data sets and use a model and train on that data set and see the accuracy. So this particular step creates the train step, whether all the gradients and and the input data sets are computed together and optimized for the minimum loss. And at this step, it runs for 3 iterations. So first iteration is finished, and then 2 more iterations, and then our program is done. Now, since this program is running on GPUs, we can see the utilization should be more than 0. So here the GPU utilization was 0, only the memory was allocated. And now, since our program is running, it's 14% usage of GPUs. We can also look GPU utilization on these plots as well. We just click on these plots, and then we see these plots refresh themselves. We can see the memory usage is 6 gigabytes here, and also the utilization Has our program finished running? Okay, and the program has finished running, so it's not showing the utilization currently. Now we also got the plot for the loss, and in the same way, different models with TensorFlow can be created, and the GPUs can be used. We saw that how the memories are allocated. To show the usage of TensorFlow, we will use another notebook, which is called model sharing. Let's look at the model sharing technique. We have one dedicated notebook for it, and it's called model sharing notebook. In machine learning, we have lots of packages which can be used. For example, scikit-learn, TensorFlow, PyTorch, and so on. All these packages let us create different models for doing machine learning, training on data sets, and then after training, they all create a model. These models can further be used for predicting new instances of data set, or these models can also be extended when new data sets come in. Therefore, we should have a common way to store these models and also share them and to get the same results back as we get from the original model. This has been made possible through ONNX technique. This stands for Open Neural Network Exchange, and it provides a format .onnx in which our scikit-learn, TensorFlow, Keras, all these models can be converted to, and then they can be used, for example, for predicting new instances. We will see a couple of usages of the ONNX model with scikit-learn and TensorFlow. First of all, we will go for scikit-learn. We need to create a model, for example, a trained classifier in this cell, and the classifier is random forest classifier, and it produces 97.3% accuracy on test data set. Now we should convert this classifier object into ONNX model, and this cell will achieve that. We will run it, and this will create a folder, and that folder will have the ONNX model. The folder is created here, the scikit-learn model, and when we open this folder, we have this trained model saved as ONNX format. In this cell, we will use the same ONNX model and see if we are getting the same accuracy as we got with the original model. Let's try to extract this model and then do the prediction. Here we are doing the prediction on the test data set, and we see that we are getting the same accuracy score, 97.36, what we got here. It proves that the models can be safely converted to ONNX format, and it can be converted back, and the results remain the same. We can also delete these file here, download it and then delete it. We can also then upload, and we get the same accuracy. You can try it on your own. In similar way, we use the ONNX format for TensorFlow models. First, we need to import the relevant packages in this cell. Let's go back to the notebooks. It will go back. We discussed that we need to limit the usage or the memory of GPUs used by TensorFlow. We saw that in the previous example. Here again, we need to do the same by restricting the usage of memory, GPU memory by TensorFlow. Here we again set it to 5,000, which is 5 gigabytes of memory. and we run this step, and we download the data set which we will be using, and we create a model here, and all the relevant code we use. For example, in this step, we are computing the gradients and then applying the gradients on the variables. And then we compute the loss by propagating the error back through the neural network architecture. Then we compute the train and test accuracy here and report back the accuracy. These steps are already running. The training step runs for 5 epochs. We go to the notebook folder again, and this is still running. Now we saw epoch 1 is completed, and we get a train accuracy of 95.8 and test accuracy of 97.8. It will run for 4 more epochs. Second epoch is also finished. We can also see the utilization of GPUs by typing the command NVIDIA SMI, and we see that our GPU usage is currently 26%. Previously, when no deep learning program was running, it was 0. We can also see the usage of GPUs by using these buttons showing the GPU utilization, and then GPU memory and the machine resources as well. We can see the CPU usage, and then was the memory usage of the program, and other plots as well. You see the memory usage of GPU is 6 GBs. Let's go back to our program and see if, so we have finished the 5 iterations, and we note that the test accuracy at the end of 5th iteration is 98.45%. We save the model as ONNX loaded model, and in this step we have the ONNX model already saved. Now we should retrieve our model back from this format and try to do the predictions, which we'll do in these cells. These cells load the model, and then this cell use the loaded model and do the prediction. For example, in this particular line, when we say tf loaded model.run, and the training is false, which means it's running on inference mode. We will see the accuracy reported here in a minute or so. And in the meantime, we can see the usage of GPU, which is now reduced to 2%, because currently we are doing the inference, which is not putting a lot of load on the GPUs. So what we are trying to verify here, we have achieved an accuracy of 98.46% here for test dataset, and with the retrieved model, it should also get the same. And when they're same, we can say that we are saving the TensorFlow trained model in a good and reliable way, which can be shared with other users, and they can use the model in the same way. I hope to get the results very soon. So we can see the test accuracy. What we are getting now is 98.46, which we were getting here. 98.4599, which has been rounded off. And the loss is 0.0616. And here also we are getting 0.016. It says that we are saving the model in ONNX format in a reliable way. And these models can be shared and can be reused again. We discussed that using BioBlend APIs developed by the Galaxy community can be used to connect with Galaxy. Galaxy has histories and workflows, datasets, which can be accessed using these BioBlend APIs. We can also use BioBlend APIs from our notebook, which is already installed. And we can import it as shown in the cell. We can get our key, our user token or API token, which you get after you log in or create an account with Galaxy. And the data sets that we are creating here with this notebook can be directly saved into Galaxy history using this command, which is called put. And we give the path to the data set that we want to upload and what's the type of the data set, and it will be uploaded. This particular data set is stored in data folder, and we have this data set which we will upload it to our Galaxy history by running this cell. So this cell has finished running, but data set may not be uploaded very soon. We see the file is already created and it will be uploaded very soon. There are lots of other APIs which can be used for connecting it with Galaxy. You can create a new history, and then you can save your data set in a new history. For example, we can create a connection to Galaxy, and we can save our data set, the same data set in the new history. We can go to Galaxy, and since we want to see all histories, we can click on view all histories, and we see a new history has been created here, and this data set is still not uploaded, but it will get uploaded soon. In this way, using this notebook, Galaxy histories can be accessed, and new Galaxy histories can be created, and data sets can be uploaded using put command. These were all about the notebooks showing different features of the project. We also discussed about how we create, how we can create a workflow of notebooks. This has been made possible by using Elira AI plugin, in using which we can create a pipeline of notebooks. We see we have 4 notebooks, and we can create a pipeline here. This pipeline can be created on the editor by just dragging and dropping these notebooks and then connecting them together. There are 4 steps of this pipeline. First one is to load dataset and then pre-process it. And then we apply machine learning techniques on the pre-processed data. And finally, we plot the results. We have this pipeline, and this can be run using this play button. And we just click here. And then it's showing a pop-up showing the name of the pipeline. And then since we are running this pipeline on the compute resources allocated to the interactive tool job, therefore we have chosen local runtime option. These pipelines can also be run on Kubernetes, but we have not yet explored that option, but it can be explored in future. We click on OK, and then the pipeline will start running. It will create a folder, data folder, and then in that folder, all the intermediate data sets would be stored, just like Galaxy does. we see that the data folder has been created, and as soon as it finishes, it says job execution succeeded. Just click on OK, and then we move to the data folder, and we see that we get a plot in this way. And this plot was created as a last step, which was the plot results notebook. And this notebook already has this plot. In this way, we can create pipelines of several notebooks, and each notebook will contain one particular part of the whole machine learning analyses. With this, I would like to conclude the demonstration of the interactive tool, which opens Jupyterlab notebook. And this notebook is prepackaged with lots of softwares for supporting machine learning research. Thank you. And I can take questions now.